Well, it's 10 o'clock, so we can go ahead and get started. Thank you all for joining us for another edition of the Long Coffee Break. My name is Bill Rohn, and I'm a senior sales engineer with Long. And today, we will be talking about Oxygenate Energy Recovery Ventilation. We are lucky enough to be joined by Brian Sinnett, Regional Sales Manager with Oxygenate. Thanks, Brian. With that, I'll hand it over to you.
Thanks, Bill. I appreciate it. As Bill said, my name is Brian Sinnett, Regional Sales Manager with Oxygenate. Oxygenate is a ventilation system company building energy recovery units and split DOAS units in Vancouver, British Columbia, Canada. Today we're going to talk about ventilation with electrification, specifically energy recovery and 100% outside air DOAS units in cold climates like Denver. You know, in the past, the way to design a ventilation system predominantly, especially in cold climates, was to put a packaged DX unit on the roof with gas-fired heater. Done, simple. Now, however, with electrification, we have to come up with a different solution. That gas-fired heater that we used to use is no longer able to be used with electrification. So then the question becomes, well, what do I do for this ventilation system, particularly in a cold climate like Denver's? Well, one option would be to use electric heat. But in order to create a 75 to 80 degree delta T with an electric heater and heat all that ventilation air is going to consume vast amounts of power. So what other options? Well, we could look at a packaged DX heat pump system. Provides heating and cooling with the reversing valve in the refrigerant system. The issue with those packaged DX heat pump systems is once you start getting into the 30 degree or maybe even 40 degree Fahrenheit outside air temperature, you have reduced or possibly no heating available. So they're not very good in cold climates because of the lack of heat when the outside air temps start dropping. So what else? Well, that's when we start looking at energy recovery. Energy recovery becomes very important when you're trying to do ventilation in a cold climate and stick with electrification principles. Now, why is energy recovery so important? Well, if you take a look at that graphic on that slide, you can see that 0 degree air in Denver is actually going to be heated up with the exhaust air to 52 degrees. So let that sink in a minute. We're going to take that heat out of the exhaust air that we would normally be blowing outdoors, and we're going to transfer 70% or more of that heat to the incoming outside air. And as shown here, we're going to do it with a stationary plate heat exchanger. No belts, motors, seals, etc. Zero cross-contamination in a plate heat exchanger, and we're going to pick up 52 degree delta T on that incoming outside air. So once we've done that, now we've got 52 degree air. Well, it's much more simple then to heat that 52 degree air up to whatever temp you might want to deliver to the space. Do you want to supply 60 degrees? Do you want to apply 70 degrees? Do you want to supply 80 degrees? Now we can use electric coil, a VRV DX coil, hot water coil, a number of different options to do that final trim heating to bring that ventilation supply air up to the temperature that we want. So let's talk for a minute about plate heat exchangers. We only utilize plate heat exchangers for several reasons. First reason is it allows us to build a very low profile unit. Unlike a wheel, which is a lot taller, I can make a low profile unit that's about a third of the height or less by using plate heat exchangers. The other portion, as I mentioned before, is that I have no moving parts. It's strictly a stationary device with zero cross-contamination that I blow exhaust air through and outside air through, and I recover vast amounts of energy. So if we think about plate heat exchangers, we have to ask the question, do we want to use an HRV, a heat recovery ventilator, which is sensible only, or we want to use an enthalpy device, transferring both temperature and moisture? Commonly, in cold, dry climates like Denver, the first answer that comes to people's minds is that, well, it's a dry climate, so I don't need moisture transfer. I'm not trying to do a job in Texas or Louisiana where it's high humidity, so I don't need moisture transfer. The thing to think about there, though, is that sensible only heat exchanger is comprised of aluminum plates. Those aluminum plates are going to start developing frost at around 20 to 30 degrees outside air temp, depending upon how much moisture is in the exhaust air. So Denver, with a design condition of 0, I would be spending a lot of hours running a preheater, whether electric or hot water or whatever, running a preheater to make that incoming outside air no less than the frost temp, which again would be between 20 and 30 degrees. So a lot of hours of running a preheater to make sure I don't frost. Conversely, if I look at an ERV, there's a couple of advantages for an ERV, which again is both sensible and latent transfer. A few advantages to using that ERV in a cold, dry climate like Denver. First one of which is the frost temperature is much lower than with that aluminum device. Here we're talking about an enthalpy device using a polymer film. It's a thin plastic membrane. It allows moisture and temperature transfer. Still 0 cross-contamination in the core. But the benefit is, rather than a frost temp somewhere between 20 and 30 degrees, now I'm talking about a frost temp somewhere between -10 to +5 degrees. So in Denver climate, depending upon how much moisture there is in the exhaust air, I may not need to run a preheater at all. So I can eliminate all that preheat energy that I would have to have with that aluminum HRV. The other benefit too with an ERV is that it helps to transfer moisture that's in that exhaust air back into the building during the winter. So I don't have to bring in that cold, super dry air, because I'm going to transfer whatever moisture, about 60 to 65% of the moisture of the exhaust air is going to be transferred over to the incoming outside air and brought back into the building. So it helps not only occupant comfort levels, because it keeps some moisture in the building in the winter, also helps with finishes. You don't get such dry conditions for the wood, etc., the finishes in the building. So a few advantages to using an ERV in a cold, dry climate like Denver, even though you don't have to be concerned about humid summertime. Other things to think about. So if we look for a minute about that polymer membrane that I mentioned, so it's a thin plastic membrane. It has tiny pores in it that are just big enough for a water molecule to move through. So it transfers temperature, but it also transfers moisture from the more humid airstream to the more dry airstream. And that's what allows it to transfer that moisture back and forth across that barrier. Still no cross-contamination in the heat exchanger. It is totally separated. Exhaust air is totally separated from the incoming outside air. At Oxygenate, we make a number of different kinds of energy recovery units, from smaller energy recovery units that'll fit above the ceiling at 16 inches or 18 inches tall, clear up to 10,000 CFM energy recovery units that you might put out on the roof or put in a mechanical room. So anywhere from 325 CFM clear up to 10,000 CFM energy recovery. And as you'll see in a minute, you can add coils to any of these energy recovery units. When I say coils, I mean electric coils, hot water coils, chill water coils, DX coils, VRV coils. So I can do a number of different things with the final heating and cooling of that ventilation air, and then blow it right into the space at any condition I want. And finally, we make a split DOAS unit. Can be hot water, chill water, or could be VRV DX, but it's 100% outside air, what I call brute force heating and cooling. No energy recovery. Use this for kitchen makeup. Use it for makeup air when I've got, let's say, fume hoods or separate exhaust. But it's 100% outside air with, like I said, chill water, hot water, and or VRV DX heating and cooling. All these commercial units from Oxygenate come standard with a packaged Distech DDC controller with BACnet integration with a BMS. They're all double wall foam injected panels. We always use ECM direct drive fans for all the fans. So they have commonality in the construction and the attributes for all of them, built like a modular air handler, even clear down at 325 CFM. Here's a little bit more detail on one of our newest units called a Ventum Plus, 1200 to 10,000 CFM, can be HRV or ERV, and in it we can integrate heating and cooling coils. So built right into the box, whether you set it on a curb or set it in a mechanical room, you can have heating cooling coils built into it, and it uses a stacked core array with counterflow, very high efficiency counterflow heat exchangers. Here's that same Ventum Plus model in its finished wiring stages. You can see it's roughly 8.5 feet tall by about 8 feet wide at 10,000 CFM. And this one, you can see it's got integrated coils. You can see the coil stub outs here in the picture. So the way this is laid out is on the left-hand side, you've got a fan and a filter in that section. Next to that, you've got a coil module. So here's where you have heating and cooling coils of various types. Moving to the right, then you have those counterflow core in that stacked array, like I showed you before. You've got another preheating module. If you need a preheat, for instance, like I said, maybe I need to avoid frost, different reasons that I might need to use a preheat module. And then I have on the far right-hand side, the fan and filter module for the other airflow. And like I said, we can take any of our energy recovery units and integrate coils with them, whether it's coils located down the duct or coils connected directly to the energy recovery unit. The benefit there is then I get the advantage of the pre-cooling and preheating with the energy recovery cores, and then I utilize heating and cooling coils to make that supply air any condition I want. So I blow my ventilation air directly into the space, and then I use the rest of the equipment, whether it's fan coils or water source heat pumps or whatever. I use that to strictly handle the space load. So you fully handle the ventilation load with the ERV and coils, and then you handle the space load with the other HVAC equipment. Here's an example. This is a 1500 CFM ERV hung on a wall. And you can see the supply duct comes around, goes behind Johnny, one of our other regional sales managers, goes behind him, and then you've got a hydronic heating coil, so a hot water heating coil there in its final position. Here's another example. This one actually is the energy recovery unit. This is our counterflow Ventum ceiling hung unit, 18 inches tall, up to 1,000 CFM. And here you can see it's got a VRV heat pump system with a VRV heating and cooling coil. We do a lot of VRV heat pump heating and cooling projects in cold climates because you can provide way more than enough heat with that VRV outdoor unit. I can make that supply air temp as high as 110 degrees, and I can make it as cold as 48 degrees in cooling. So I can do a lot of different things with this. I can add hot gas reheat to it if I want, if I shift to a heat recovery outdoor unit. So just a lot of different options when doing energy recovery and adding VRV heating and cooling. We also can locate those coils down the ductwork. So maybe you don't want the coils connected directly to the unit. Maybe there's not enough space in the overhead or space in the mechanical room. So you can locate those coils down the ductwork. Here's an example. They flip the energy recovery unit up on its edge, brought the supply duct up, turned 90 degrees, and then here's a VRV heating cooling coil, an access section, and then an SCR electric heater as post heating for dehumidification in the summer, also as backup heating in the wintertime. Now, this project was in Iowa at the Fort Dodge Community Health Center, extremely cold winter conditions, and they wanted backup heating in case anything went wrong with the DX system. Just some other examples. We do a lot of open ceiling concept projects because, again, we've got that double wall foam injected panel, which dramatically reduces sound, and also those low sound ECM fans. I said we make that Terra DOAS, so it's a split DOAS system or a hydronic DOAS, 100% outside air. If you can't get the return air back to use an energy recovery unit. When you do use that TerraDOAS unit, if you're using VRV, you will need preheat, just because of the VRV requirements for minimum entering outside air temp. Just as a recap, we've got Oxygenate makes a number of different ventilation units, as you've seen. And when you're looking at doing ventilation and taking electrification into the mix, it requires a different approach than what you've typically used in the past. And ERV, as you've seen, can become very important when designing ventilation systems with electrification, because I can get massive amount of preheat. I can recover, like I said, roughly 70% of that sensible temperature from the exhaust air and preheat that incoming outside air. And so just keep in mind that Oxygenate has a number of different solutions for ventilation systems, as we've talked about today. If you want any more information, if you want to talk about ERV versus HRV, or you want to talk about any of the solutions we talked about today, please contact your Long sales rep to set up a meeting, whether Teams or in person, or you can email me directly. My email address is brian@oxygenate.ca, again, because we're located in Canada. I personally live in Raleigh, North Carolina, but .ca because the company is in Canada. Thank you.
Thanks, Brian. I really appreciate it. Thank you all for joining us on this coffee break. Please reach out to your Long sales engineer for additional information on Oxygenate solutions. Please join us on January 11th when Travis Cowan will be discussing sorbent ventilation technology. Thank you again for joining us, and have a great day.